Hi, so welcome back again. So this course is continuation of the last semester course, graduate analysis 1, which was taught by Krishna. And we will cover some of the basic functional analysis and some fundamental theorems of analysis like Karzala-Scully theorem, Stone-Weierstrass theorem. All those things you might have seen it earlier, but we will cover it anyway. And then we will do some Hilbert space theory, operator theory and operators on Hilbert spaces. And finally, we'll end this course with the spectral theorem for a compact normal operator. So this is exactly what is prescribed in the syllabus of the CMA website, and that's what I will do. So I don't really plan to do anything more. And so part of this course, nearly half of this course will be taught by me. And 1/4 of this course will be taught by Nirupama and Shruti, who are postdocs here. And I will be anyway sitting in those classes. Okay. So the evaluation is through some assignments, and we will have 2 exams. And I would prefer to have offline exams. So I don't know when that will be possible, and we'll think about it later. Okay. So let's start. I will share my file. I will share the iPad. I think it should work okay today. Yeah, so you want it this way, someone wanted it this way, so see, okay, it's fine. Okay. So you have seen some Banach space theory. Okay. So we will be discussing, it's X need not be a Banach space. Let X be a normed linear space. One second. And that's a problem. Okay, so let X be a normed linear space. And by this we mean X is a vector space, and we have a norm, which is a function from X to the positive real line 0 infinity, which satisfies those 3 axioms, so which you know already. So norm X equal to 0, if X which is equivalent to saying X equals 0, it satisfies the triangle inequality. Norm X plus Y is less than or equal to norm X plus norm Y, and norm of alpha X is mod alpha times mod X for any alpha. So the vector space can be over, as I mentioned here, the vector space can be over complex plane or real line. So depending upon that, the alpha will be either C or R. Okay. Okay. So then we have the notion of so the morphisms for vector spaces are linear functionals. Okay. So if we have any object, then there will be morphism between those objects, and so here the objects are linear functional. Are you disturbed by the sound of the fan? Is that okay? This fan makes some sound, so I put it off, but then I have to put it on. If you have some problem, you tell me. Okay. Okay. Maybe I will increase the speed. Okay, so but then when we consider the norm linear space, it's not just vector space, we have a norm structure also. Then we would like to consider what are called, we would like to, functional analysis is a kind of combination of algebra and also the topology. So we have a norm which gives a topology, And we would like to consider continuous linear functional. Okay, we are not just linear functional. And those continuous linear functional and linear functional is continuous if and only if it's bounded. That you know, I mean, a linear functional is continuous if and only if it's uniformly continuous, if and only if it is continuous at some one point, and it's equivalent to saying it is bounded. It is bounded by some. I mean, it is. I mean, it's not actually a bounded as not as a function. It's not bounded. This is what is the definition of bounded linear function. There exists a k such that norm of phi of x is less than or equal to k times norm x. And we will define norm phi to be this infimum of all those k's. All those k such that norm of phi of x is less than or equal to k times norm x. And this will also be equal to supremum of norm x less than or equal to 1. And you must have seen this proof. Norm x less than or equal to 1, the mod of phi x. Okay. And which is also equal to supremum of norm x equal to 1, mod of phi x. Okay. So these things you must have seen. Okay. So now there is a fundamental question. The basic question is if you have a Banach space, if you have a non-linear space, how do we know that there actually exists a bounded linear functional on that? Okay. So that we don't know actually. We don't know whether it exists, but it's philosophically we are actually assuming that it exists. But then that actually follows from the axiom of mathematics. See, mathematics has some basic assumptions. You might have heard that empty sets exist, and the set empty set is not equal to set containing empty set, which is a singleton element. And beyond all these axiom in mathematics, the mathematics we do in our courses, we assume something called an axiom of choice. So, there are some people do mathematics without assuming axiom of choice, but usually it's not accepted at mathematics. I don't consider that as mathematics. So in the mathematics we do here, we assume something called an axiom of choice. Axiom of choice says the following: if we have any collection of sets, if you have a collection of sets indexed by some other indexing set, then we can choose one element from each of those sets. We can define, if you have a collection of sets, something like I, if you have a collection of sets, so we have a I, x in I, you have a AX, which is a set. Okay. Then you have a function from this I, taking values in disjoint union of A, such that f of some I is in, f of x is in AX, something like this. You can form a tuple with these things. So this is what, we are not going to discuss this axiom of choice, but this axiom of choice is something assumed in mathematics. This axiom of choice is equivalent to something called Zorn's lemma. So you can actually assume Zorn's lemma and prove this axiom of choice, or you can, you can prove Zorn's lemma from axiom of choice. And you have to do, you can assume one of that, and then prove the other one. So this, whatever the question, we asked, that whether there exists a bounded linear functional on a non-linear space, that is actually guaranteed by the Zorn's lemma. If you don't assume Zorn's lemma, then there is no reason. So you can actually assume this existence of bounded linear functional, continue to do mathematics, do functional analysis. But then we can't have different axioms for different branch of mathematics. So we have this axiom of choice. From that, the Zorn's lemma will follow. And from Zorn's lemma, there is a theorem called, the theorem we are going to prove, the Hahn-Banach theorem will follow. And that ensures that there exists a bounded linear functional. So if we have a finite dimensional vector space, in finite dimensional, all linear functionals are bounded. So you don't have to worry about boundedness or continuity. So in finite dimension, always there exists linear functional, and that will be automatically bounded. That you can always, if it is finite dimensional, there will be a basis. Using those bases, you can define, everything will be a scalar linear combination of the basis element. And using that, you can define a linear function. So if it is countable also, you can do something. But when usually a Banach space will not have, which will follow from Baire category theorem, which we are going to prove soon. So usually in the Banach space, the dimension will not be countable. It will be uncountably infinite. Okay, so if you have infinite dimensional Banach space, these things are not clear. So that is what we want to. We want to ensure there exists bounded linear functions on our Banach space. For that, we are going to prove the following theorem in this class. Okay. If you have questions, please ask me. I am not at all sure whether anybody is listening to this talk. Okay. I mean, I'm not. It's not clear to me whether there's an audience here. I see so many people here, but if you ask questions, it will be nice. Okay. Okay. So this is the theorem we want to prove. The following theorem. So X. So here X need not be even normed linear space. So first we will prove this theorem for a real vector space, real normed linear space. Then we will prove it for the complex normed linear space. And we will be mostly dealing complex normed linear space in this course. Okay. So X be a real vector space. It's a vector space over real field. Okay. And P is a functional. It's a function from here to from X to 0 infinity. It satisfies the following, such that one. This is what is called the sublinearity property, something like triangle inequality. These things. So for all x, y, x. Okay. And the second property is P of Tx is equal to T times P of x for all T positive T. Okay. So we have a function P from x to 0 infinity which satisfies these two properties. This property is called sublinear. And this is some sort of linearity for positive elements. This is usually called a sublinear functional or a Minkowski functional. Okay, sublinear functional or Minkowski. The name is not important. So we have a real vector space and we have a Minkowski functional satisfying these properties. Okay. Now suppose let x naught be a subspace. Okay. And phi naught from x naught to real line is a linear functional such that, so we are not assuming non-linear space, it is just a linear functional which is dominated by this Minkowski function such that norm of, so it's just mod of phi naught x is less than or equal to P of x. P takes values, positive values, so I don't have to take mod for all x in x naught. Okay. So we have a linear functional defined on this subspace, which is dominated by the Minkowski functional. Then there exists a phi, which is defined on the whole non-linear space to R, a linear functional, such that this is also dominated by the same Minkowski functional, and phi restricted to that x naught is just phi naught. Okay. So this any linear functional which is defined on a subspace and dominated by a Minkowski functional can be extended to the whole space, bigger space, still still dominating by the same Minkowski function. Minkowski function is defined on the whole space. Okay. Okay. So the problem with keeping this iPad horizontal is you cannot see much in the screen. So if I keep it vertically, you can see more, but then it will be small. The screen will be small. It's up to you. So since someone asked, I'm keeping it like this. So you can't see much in this. Okay, let us prove this. So this is the statement of the theorem. Statement of the theorem is if you have any linear functional which is defined on the subspace dominated by a Minkowski functional which can be extended to the bigger space, still dominated by the Minkowski functional. To prove this, we need what is called Zorn's lemma. Okay, So I recall what is John's lemma. I am not going to prove John's lemma. You must have already seen, I mean, I am sure you will not have, unless you are interested, you would not have seen the proof of John's lemma from Axiom of Choice. And I mean, it's not taught in any of the courses, but it's assumed throughout. So it's better to see the proof, but it's not proved in any of these courses. So I have to recall the John's lemma. So the ingredients for John's lemma are the following. So we need some definitions for John's lemma. So, okay, let script P be a partially ordered set. By partially ordered set means there exists a relation on that. That means script P with a greater than or equal to. Okay. So this is just a relation. This greater than or equal to sign is just a P is just a set. Script P is just a set, and this greater than or equal to is just a relation. You know what is a relation? It is just a subset of P cross P. Okay. This is a relation. And this means that x is reflexive, x is less than or equal to x, and x is less than or equal to y, and y is less than or equal to z, x is less than or equal to z. Then the important thing is it's antisymmetric. It's a relation which is antisymmetric. And y is less than or equal to x implies x equal to y. Okay. I mean, let me not recall what is partial. I am sure you must be knowing this. Okay, this is a partially ordered set. Then the C contained in rho, C contained in P is a totally ordered set, which is also called as a chain. Ordered, what is spelling of order? Ordered set, okay, whatever. Set or a chain. A totally ordered set is also called as a chain. Okay, it's a chain. If for all xy, either x is less than or equal to y, or y is less than or equal to x. So if you have a partially ordered set, there is no reason two elements can be related. I mean, they need not be related. There is no reason they are related. But then in a totally ordered set, if you have two elements, then either x should be less than or equal to 1, or y should be less than or equal to x. For example, in the real line, you have the usual less than or equal to relation, which is a total order. On the other hand, if you have a collection of subsets of some big set, then you can have you can say something is less than or equal to the other set if one thing is contained in the other, and that's not a total order. Okay, you can have similarly, you can have some partial order on complex plane or any tuple, or you can see that all usually the partial order need not be a total order, but there can be a subset where it is a total order. Okay, so this is a chain is a totally ordered subset. Okay, it's a subset of that partially ordered set. Okay, then an element x in. So if we have, this is the definition. Let me point 1. This is 2, 3. So if we have a C contained in P, then an element x in P is an upper bound. Upper bound can be defined for any set, but here let's take it. Upper bound for P, for C, if y is less than or equal to x for all y in C. Okay. This x dominates all elements in C. Okay, that is an upper bound. So maximal, so this is an upper bound. So, if you have an open interval, then you know what is the upper bound of that. Okay. So maximal element is something different. An element x naught in C. So this does not require a subset. Upper bound is for a subset, and an element x naught in P is maximal. It's maximal. maximal element, there does not exist any other element which dominates this element. It need not be the case that maximal element is greater than or equal to all the other elements. There may not be any relation with the other elements. It is just that there does not exist anything which is greater than this. So maximal, if y is greater than or equal to x naught, implies y equal to x naught. Okay, so there is nothing which is greater than this. There is nothing which dominates this. So these are the ingredients for the, these are the notions we need to state the Zorn's lemma. Zorn's lemma is we have a partially ordered set, then we have something called a totally ordered subset, then we have an upper bound, then we have something called a maximal element. So this is the statement of the Zorn's lemma, which we will be using. Okay, I'm sure you must have seen this Zorn's lemma somewhere or other. Okay, where will it be used? Even if you have done topology, Tekhanov's theorem is proved by Zorn's lemma, or what else? I don't remember. So I'm sure you must have seen. Okay, Zorn's lemma. Okay, so P smaller than or equal to is a partially ordered set. Set. If so, we have already defined all these things. If every chain or every totally ordered subset, every chain in P has an upper bound, then P has a maximal element. That's all. There is no need that partially ordered set has a maximal element. This just says that if every chain has a upper bound, then it has a maximal element. So to prove that there exists a maximal element, we will prove that every chain has an upper bound. Okay, that's all. It's just a, existence theorem. Okay. So this is the statement of Zorn's lemma, and using this Zorn's lemma, we want to prove this Hahn-Banach theorem. This is proved by Hahn and Banach. Okay, so that's proof of the Hahn-Banach theorem. So we have a phi naught defined from x naught to real line. Okay, and we have the linear functional. We have phi naught x is mod phi naught x is less than p of x for all x in x. So we want to use Zorn's lemma to prove this. It is essentially Zorn's lemma. This theorem is essentially Zorn's lemma. So we want to have a partially ordered set. Then we will consider the chain, and we will prove that every chain has an upper bound. Then it will be once we prove that, then Zorn's lemma ensures that we have a maximal element, and that maximal element we will prove that is actually equal to the whole space X. That's what we want to do. Okay, so let rho equal to all rows y, and let me use this notation where y is a subspace. So x naught is contained in y, contained in x, and is from y to r, and it satisfies this relation. X is less than or equal to p of x. Okay, and restricted to this x naught equal to the original phi naught x. So we consider all extensions. It may not exist, but the whole space x naught with phi naught. So this is not empty. Okay. So in Zorn's lemma, we need it to be non-empty, of course. It's a non-empty partially set. Okay. And clearly this is non-empty because x naught phi naught is in this. Okay. So this is not non-empty. This is not equal to empty. And so we are considering this partially ordered set is all extensions of this phi naught, such that it is dominated by the Minkowski function of P. Okay. And we define some y1, chi1 is less than or equal to y2, chi2, if y1 is contained in y2 in the natural partial order, and chi2 restricted to this y1 is equal to chi. Okay. So it is just the, I mean, it is an extension of chi1 to chi1 to y2. Okay. Chi2 is just an extension of chi1 to y2. So this is the partial order. So suppose this C equal to some y is a chain. Okay. Contained in the row is a chain. That is, everything is related, and I mean it's a totally ordered set. Then you can take some bigger y prime equal to the union of all those y's, y in this. Okay. Yeah. And if and define, maybe I will use the I mean the symbol. Okay. That's easier. Suppose this yi, okay, I9 is contained, is a chain, is a totally ordered set. Okay. Then define y equal to union of all those y's. Define from y to real line by chi of, I mean, if you have any y equal to chi I y, if y is in some yi. So this y may be in two chi I and chi, I mean, it may be in yi and yj. But then this is a totally ordered subset. So yi has to be inside some yj, or yj has to be inside yi. Then they will coincide. I mean, we have assumed that they are extension of extension of the whichever is the smaller one. Okay. So because of that, it will follow that this is well defined. Then chi is well defined. Well defined. And this is the upper bound. This y chi is an upper bound. For that chain, we called it C, no? C. Okay. So we have proved that every totally ordered subset, every chain has an upper bound. So Zorn's lemma implies there exists a maximal element. In this. Okay. So call that maximal element as y. There exists a maximal element. Let me call it as y1. So the claim is this is the whole space. So claim, I mean, we are done if claim is y1 is equal to x itself. If not, there exists x naught, which is in x minus y1. So there is a x naught, which is not in y1, but in x. Okay. And which is not equal to 0 also. Okay. Which is not, is this okay? Which is not equal to 0. Okay. That's what it means. It cannot be 0. Okay. So, see, the point is, if we have any linear function on the subspace, we can always extend to one more dimension. We can add one year. I mean, we can add one dimensional subspace to that. We can take the direct sum. We can add means it's not union, it's a direct sum. And then we can extend to that. That is not a problem. So that is what we will do here. We can, if this is not whole of x, we can add one element, this x naught, the real one-dimensional vector space generated by this x naught to this y1, and we can extend this linear functional. It is not just an extension; it satisfies those dominants by the Minkowski functional also. That's what we want to do. Okay. So now consider y2 equal to x direct sum this tx naught or x naught. I mean, this is by definition, this is all those x plus tx naught, where x is in, sorry, this is y, no, sorry, this is y1. Yeah, when I make mistakes, please point out. Okay, I will know that you are listening. X is in y1 and t is in r. Okay, so this is just the vector space direct sum of this y1 and the one-dimensional subspace generated by this x naught. Okay, that is this y2, and we want to extend the linear functional. So we have there exists a maximal element. That maximal element we call it as y1 and chi1. Okay, y1. And we want to prove that this chi1 is the required element. Okay. Okay. So now we want to define a linear functional on this y2. And if we define a linear functional y2, which is actually an extension of our maximal, whatever we call it as maximal, the chi1, and if it is dominated by the, I mean, if it is dominated by the Minkowski functional, then this is not the maximal. It will contradict the fact that it's a maximal element. That's what. So we want. So then we will prove our claim. So for that we need to see, if we want to define a linear functional on this y2, all we have to do, we already have a linear functional as y1. We have to define only on this the rx naught, and to do that we only need one real number to do that. See, suppose, so let me say this. Suppose t naught is some real number in R, real number, then we defined on this x plus t x naught equal to, we already have this chi, I called it chi1, okay. Chi1 of x plus t times t naught. Okay. For any t naught in real line, this defines a linear function. You can see. Okay. All we need to verify is this. We have to choose a t naught such that it is dominated by the Minkowski function. That's what we want to do. So we want, I mean, we want to choose t naught such that this is dominated by the phi of x plus t x naught is less than or equal to, which is equal to chi1x plus t naught, which is less than or equal to this p of x plus tx naught. That is what we want, right? This is what we want to prove. So what does this mean for t? Suppose this is what we want. Okay, we want this. Okay. Now suppose t is less than, t is greater than 0, okay, greater than or equal to 0. Then, so we want this to happen. Then chi1 of x plus t naught is equal to, we can take the t out. Okay, chi1x x by t plus t naught. We want to choose this t naught. Okay. We want this to happen. So this is less than or equal to p of t times x by t plus t naught. This is what we want. Okay, we want this. We want this term. I mean, we can replace this x by t by some y. That is, we want chi1 of y plus t naught is, I mean, this t is positive, so you don't have to worry. This is less than or equal to p of y plus t naught. Right? This is what we want. For yeah, that is what we want. Because t is positive, this is okay. I mean, when t is positive, if this is less than this, since t is positive, this is okay. On the other hand, so this is what we want. Okay. On the other hand, for t less than or equal to 0, less than or equal to 0, we need to take minus t outside. Okay. So chi1 of x plus t naught. T is less than or equal to 0 now, which is equal to minus t into chi1 of x by minus t naught. Minus t. Okay. So now minus t is positive, so we want this to happen. Minus t times t of anyway. I mean, because this is equal to p of x plus t. Okay. This is what we want. Minus t into p of x by minus t naught. Okay. This is equal to, of course, p of x plus t naught. Okay. So we want this to happen. That is, we want chi1 of y minus t naught is less than or equal to p of y minus t naught. Right? If chi of this is, I mean, I'm just, instead of x by x divided by minus t, I'm just taking it as y. This is true for all y we want. They called it as y1, no? Yeah, y1. Okay. Is this okay? Do you want the screen to be the other way or this way? Is this fine? Or is this proof okay? I mean, this is what we want really. We want to prove that it is dominated by the Minkowski functional. For that, this is what if we prove this, if we choose a t naught such that this happens. We haven't chosen a t naught. For every t naught, we will get a linear functional. Okay. So if we choose this t naught, which satisfies these two conditions, then that is enough. Okay, that's what I'm saying. So it should be possible to choose a t naught like this. Okay, is this fine? If you have any doubt, you can stop me and you can ask.
Yes, this is fine.
Okay, this is fine. Okay. So this is what we want to do. So for that, I write here itself. Okay. So what do you want to do? We have, so suppose let y prime is in y1. Okay. Then phi of not phi, chi is my, called it chi1, right? Then chi1 of y plus y prime, chi1 of y plus y prime is equal to chi1 of y plus chi1 of y prime, of course, because that's linear. And this is less than or equal to p of y plus y prime. Okay. Now this is less than or equal to p of Here I have written x t naught. This should be x naught. Okay. Here I have written it. Sorry, here also I have written it t naught, which is x naught. There is no x naught is the element in the non-linear space, and t naught is a number we want to choose. Okay. Anyway, I'm just going through the proof again. I mean, I will repeat that argument again. Okay. I will make the necessary changes later. So if we have any y and y prime, any two y and y prime, because chi1 is linear, of course, we got a subspace y2, and we got a subspace y1 and a linear functional chi1, which extends the original functional phi naught. We want to prove that this y1 is nothing but the whole space x. Okay. If it is not, then we choose an element x naught, which is not in y1, which is not in y1. Then using some real number t naught, we want to define a linear functional by adding this element. I mean, by adding this one-dimensional subspace generated by this x naught to this y1, and we want to define a linear functional on that. So y minus x naught. This is y plus x naught plus p of y minus x naught. Of course, you can add x naught and minus x naught there, and then because of sublinearity, because it's a Minkowski function, because of sublinearity, this is true. This is true. Now you can bring, so this is y prime. Okay. Now you can bring the y all the way, the expression with y on the one side, y prime on the other side. So this implies phi of not phi chi1. Now this chi1 of y minus p of y plus x naught is less than or equal to p of y prime minus x naught minus chi1 of y prime, right? And this side y is there, this side y prime is there. Okay, so this is true for all y and y prime in the y1. Okay. I have just used the linearity and sublinearity of chi1 and sublinearity of the Minkowski functional p. So I have got this inequality for all y and y prime. This is true. So you can take the supremum on the left hand side and the infimum on the right hand side. Still this will be true. And the supremum over all elements, right? Supremum of y in y1. Okay. This is less than or equal to infimum of all y prime in y1. This is true. Okay. Because that inequality is true for all y and y prime. So this is true. Now you can choose t naught between these two infimum, between the supremum and infimum. Okay. Okay. I mean, they may be equal, doesn't matter. Okay, you can choose a t naught between these two things. Okay. Okay. Now we want to prove that this t naught proves what we want. Okay. If this is true, then so choose t naught between these two things. Then chi1y minus t naught is less than or equal to p of y plus x naught for all y. And I mean, this y and y prime was just, I mean, just to show that inequality, we use different y and y prime. This is true for all y. Okay. And chi1, what is the other one? Chi1y plus t naught. So what is the this is less than t naught. So chi1y minus t naught is less than this, and t naught is less than this. So chi1y plus t naught is less than or equal to p of y minus x naught. These things are true for all y. So if you see precisely, this is the inequality we want. We have written here. Okay. Right. This is precisely the inequality. We want to choose a T naught such that these two things happen. Okay. So now go through the proof. Okay. I mean, wherever I have written want, you just remove it. Okay. So because I gave the argument and came back here. So now can change the proof. I don't want to change here now. No. Okay. So this implies I of we have defined. Yeah, we have defined what have we defined? We have defined a phi. Okay. Then phi of that x plus y or y or x y plus tt naught is less than or equal to p of y plus tt naught. Okay. For all y in y1 and t in r. So this contradicts the fact that that is a maximal element. Okay, hence a claim. This is the symbol I use for contradiction. Contradicts that this is maximal. Y1, chi1 or chi1 is maximal. So this implies y1 is equal to x. Okay, and we got the right element. So the theorem is proved. Okay. Is this okay? So this is essentially Zorn's lemma, and then we do some little bit manipulation, which is true, which we can do for any subspace. If we have a linear function or any subspace, we can extend to one more dimension by adding one more thing. But that is not possible to reach from one space to one subspace to the bigger space. Okay, when it is infinite dimension, it's not possible. So that's why we need Zorn's lemma. Is fine. Okay, so I assume it's fine. So this implies that if we have X is a normed linear space, then we can define this X star, all those phi from X to, oh, I haven't proved this, sorry. So we have just proved that if some linear functional defined on a subspace is dominated by a Minkowski functional, then we can extend this to a whole space, which continue to be dominated by the same Minkowski function. So now we want to prove that we can extend any bounded linear function from a subspace to a bigger space for both real and complex non-linear space. So this is the next theorem. This is actually Hahn-Banach theorem. I mean, you can call anything as Hahn-Banach theorem. Hahn-Banach theorem is there is a geometric version of Hahn-Banach theorem. You will not be seeing that, but there are other versions also. So this is also Hahn-Banach theorem. So we directly state it for complex vector space. Let's state it whichever the way. Before that, maybe I will use this notation. So X is a normed linear space. Then X star equal to all those phi from X to C over C or R is also C or R, and phi is bounded. Okay. All bounded linear functional, I'm calling it as X star. So we still do not know X star is whether X star is non-trivial. I mean, zero functional is there. Apart from that, whether there is anything, we don't know. So for that, we use the Hahn-Banach theorem. So X naught is a subspace of X, all are non-linear space. Okay, and the phi naught is from X naught to C or R, whatever. Okay. This is a non-linear space over C or R. Okay. Then there exists a phi in X star and the bigger space such that phi restricted to this X naught equal to phi naught and norm phi is equal to norm phi naught with the same norm. We can extend it with the same norm. So this is Hahn-Banach theorem. You can check, I mean, for complex function, See, there is no Minkowski functional for complex plane because there is no partial order on complex plane on complex numbers. But then you can replace this whatever this, I mean, this boundedness by some semi-norm kind of thing. See, here we will use the following Minkowski functional for real one. Phi of x is less than or equal to norm phi times norm x. So P of x equal to this norm phi times norm x. This is the Minkowski function. I mean, any constant times any positive constant times norm x is the Minkowski function. So we will use this for the real, I mean, any complex non-linear space is also a real non-linear space. We will use that fact. First, we will prove this theorem by, I mean, X is a, suppose we assume that X is a non-linear space over complex plane. And it is also a non-linear space. It's a vector space over the reals also. So we'll prove that for the real version, and then the complex version will follow. Okay. So suppose X is over real. Okay. Then take, I mean, and X is over real and phi naught from X naught to R is bounded. Okay. Take P of X equal to norm phi naught times norm X. Okay. Then you apply the earlier Hahn-Banach theorem, Earlier Hahn-Banach theorem will imply there exists a phi in X star such that phi restricted to X naught equal to phi naught, and it is still dominated by that function. So which will imply that norm phi equal to norm phi naught. Okay. I mean, it will be dominated by the Minkowski functional. That precisely means that is the norm. Okay. Any number which, I mean, it's not immediately clear. So see, the point is, if we have any, if you want to prove something is the norm of something, okay, I mean some number. So if you have a linear functional, this is just a remark. If we have a linear functional from here to C or R, whatever, if we have a C or R, okay, and suppose this is true, phi of x is less than or equal to k times norm x. Okay. And mod, so this is mod, this is just mod. And also phi of x is equal to k times norm x for some x. Okay. Then norm phi is equal to norm. Okay. I hope you know this. Okay. Because the infimum of all those k will be precisely this, right? So because of that. Okay. So here, I assume you know all these things. Okay. So here, this you initially had a phi naught which is defined on a subspace. Now we have extended it to a linear functional on the whole space x, and it continues to satisfy that inequality. That phi of x is it continues to satisfy this inequality. Norm of phi of x is less than or equal to norm phi naught times norm x. Okay. But then the already norm is attained on the smaller subspace. Okay. So so you cannot have something smaller than this which satisfies this. Okay. Because that is, this norm phi naught is the infimum. So this implies norm of phi is also equal to norm phi naught. Okay. Anyway, this is an exercise. This is something you get convinced. Okay. Verify. I have given the argument orally. Just verify this. So norm phi is equal to norm phi naught. So this proves for the real version. We want to prove it for the complex version. For that, we need the following lemma. This is an assignment for you. Okay. This is assignment. So I will give assignments in the middle of the class. So in the last year or sometimes someone had complaints over it, but I think it's okay because that's one way of making sure that you attend this or you look at this. Okay, so the assignment is the following. This lemma says the following: if we have a complex vector space, then you can take the real part of, I mean, you have a complex vector space and you have a linear functional defined on that. Okay, then you can take the real part of the linear functional that will give you a real part or imaginary part, whatever you want. Then the real part will give you a linear functional. Okay, we want to say that that real part uniquely determine the linear functional. That means if you take the real part of the linear functional, then the imaginary part of the linear functional is determined by the real part, provided it is complex linear. Okay, and conversely, if you have any real linear functional defined on that, using the real linear functional, you have a way of defining the imaginary part, and then you get a complex linear function corresponding to that. That's what this says. So suppose, I mean, this is a linear function. We have a complex normed linear space. X is a normed linear space over C, and phi from X to C is a linear functional. And no need to assume bounded or something. It's just a linear functional. And then phi1 equal to real part of phi. You just take the real part of phi. Phi takes values in complex plane. So you can take the real part of that. Then phi2 is equal to imaginary part of phi or linear functionals, of course. This is clear. Okay. And further, are linear functionals, and let me use and phi2 is determined by phi1. So phi2, I mean, the linear functional phi1 and phi2, they are defined on the whole Hilbert space. That's a whole non-linear space, which is a complex linear space where you can scalar multiply by complex numbers. There is no problem over that. Okay, so this phi2 of x equal to minus of phi1 of ix. Okay, for all x in x. If you have any x, you can multiply by ix, which is in this x. Okay, that makes sense. But this phi2 and phi1 are just real linear because you are just taking the real part of a complex linear functional or imaginary part of the complex linear functional, so which is just real linear. So you can check all these things, and this just follows immediately. You can evaluate. You can take the phi of ix, you take the imaginary part of that. That will be the real part of this. I mean, you can take the I out of phi, and the imaginary part will get multiplied by I. That will become -1, of course. So it will follow. Okay, so this is clear. Conversely, if phi1 from x to r is a real linear functional, okay, or space X is a complex vector space, but still we are assuming it's just a real linear functional, then phi of x equal to phi1x minus, I think we have to multiply by I times phi of phi1 of ix. Okay, this you have to verify. Defines a complex linear function. Okay, so I think the assignment is clear. Okay, so if we have any real linear functional, then we can define a complex linear functional in a well-defined way, and that's the only way we can do it. Okay, okay, that's what this says. Now proof of continuation. Proof. We continue the proof. So now we have a complex linear functional phi naught from x naught to c. Okay, bounded linear functional. Then let chi equal to real part of phi naught. Okay, and we want to extend this phi naught. So let's say chi to be real part of phi naught, which is a real linear functional. Okay, real linear functional. Okay. Then we have already seen that this can be extended. Extend. So call this chi naught. Extend chi naught to chi on x to r, okay, which is a real linear function, such that norm chi equals to norm chi naught. And this norm chi naught is also equal to norm phi naught. That's because norm of mod of chi naught x is less than or equal to, of course, real part of that, which is less than or equal to phi naught x, which is less than or equal to norm phi naught times norm x. But then this will be attained. I mean, you can multiply by, I mean, same trick. If you have any chi naught x, which is suppose this phi of x is a complex number, you can multiply by a number with unit modulus to get a real number. Okay. On the other hand, e power, I mean, if which we will be using it here, phi naught x equal to e power, suppose if e power I theta times mod of phi naught x. Okay. Then mod of chi naught x, chi naught of e power minus I theta x is equal to phi naught of x itself. Okay. So norm phi, I mean, this will be bounded by norm phi naught. So from this, convince yourself that mom of chi naught is equal to norm of phi naught. If you use the definition of norm, this implies norm of chi naught is norm of phi naught. Okay. Am I going fast or something? Is this clear? So if I don't see any reaction, I will tend to go fast. Okay. I'm just saying that if you take the real part of something that has the same norm. So that is what I have explained here. Okay. I return the reasoning here. Okay. Or if it is trivial, it's so fine. Okay. If you have already seen this, these things will be trivial. Okay. So now what have we done? We had a real linear function. We had a complex linear functional defined on x naught to c. Then we took the real part of that and we extended the real part to the we extended that real linear functional to the whole of x. Okay. Now we want to get a complex linear functional, and we know how to get a complex linear functional from a real linear functional. Now define chi of we want to call it phi, no? Phi of x.
Could you scroll up to the exercise once more? Could you scroll to the exercise again?
Assignment, you mean?
Yeah.
Yeah, sure.
Yeah. So in the last line, it is phi 1, right? The phi 1x minus I phi 1.
Correct. Yeah.
Okay.
We have only one
Yeah,
real linear functional. Using that, we are defining the imaginary part to be this, real part to be this. Correct. Fine.
Yeah.
Is that what you want to know? Okay. So that's what. So
yeah,
now here also I'm doing the same thing anyway. We had a complex linear functional defined on a subspace. We took the real part of that. Then which is a real linear functional, we extended that real linear functional to the whole space. Now using that real linear, which I am calling it as chi here. Okay. Using that real linear functional, I am defining a complex linear functional by the same prescription. Okay, minus I chi of ix. Okay. So this is complex linear. So now phi from x to c is complex linear. Okay. And we want to prove that this is precisely what we want, which satisfies that condition. Norm phi is less than or equal to norm phi naught. That's what we want to do. Now we have some x here. I mean, let's fix some x for x in x. Let phi of x, the same thing, e power I theta times mod phi x. Okay. some complex number of modulus 1 times mod of phi of x. Okay, then mod of phi of x equal to e power minus I theta phi of x, right? Which is equal to phi of e power minus I theta x, right? But then phi of this is real, which is also same as real part of phi of e power minus I theta x. Because this is real, because that is mod of that. Okay. So this is equal to chi of e power minus I theta x. But we have already proved that is less than or equal to phi naught times x. Okay. So this implies norm of phi is equal to theorem is proved. So this is Hahn-Banach theorem. We have some corollaries to Hahn-Banach theorem. We will see on Thursday, which ensures, it's clear now. From any subspace, we can extend it to the whole space. This is, so on finite dimensional vector space or even one-dimensional vector space, we have linear functions. So we can extend to the bigger space. So we have linear function, bounded linear functions on any non-linear space. So this is the existence theorem. Okay. So any questions? If you don't have any questions, I will stop recording. After that, if you want to discuss about any question, I will stop sharing. So it's clear now.